Okay, so in this module, it's more building on some of our exponent laws, but really it is just building understanding with them as a function. Now, you'll notice like a lot of the videos are me solving. We'll discuss it, but I actually, because it's really tough, honestly, especially online for some of these functions, is really just walking through what's already present on the module. And then obviously if anyone needs additional support, we can do that. So exponential relationships, something that you wouldn't have done last year in grade 10. We're looking at growth, decay models, and things like appreciation, depreciation with finance. And one of the best examples of an exponential relationship, I would say, is acceleration. So just discuss as a learning goals. So a key to this is y-intercept, which we'll get into, but overall the exponentials accelerate at a much steeper or flatter rate compared to linear quadratics. So for certain expressions with polynomials, you have y equals x squared, which we've already explored, is a quadratic. But what it's getting at is when your base is actually a numerical value. So for example, 2 to the power of x. What we'll do is we'll graph out some in a second with Desmos. But the key to it is this is going to basically make your function accelerate. How it differs from y equals x squared is we'll look at this as well, but y equals x squared is a parabola, is symmetry on both sides, whereas y equals 2 to the power of x does not. So you have a few different cases. First of all, y equals b to the power of x when your base is bigger than 0. So when we're looking at these types of examples, your base could be 2, 3, 4, 5, etc. There's a lot of extra information on here. Your best bet, though, is honestly to use Desmos to graph and just evaluate some of the relationships. So you can sub in exactly as you typically do. When you're doing the following calculations, just it doesn't like automatically populate. So you're just going to try them on the side, make sure everything's kind of going to terms with what it's talking about. But something as well in the thinking connection here is when exponent is negative, the power is actually on the wrong side. So in exponents, the key is we want everything to be positive. Again, you don't have to go like very far into detail about this. As long as you can sub in a point into a calculator, you'll be just fine. A lot of this discusses certain points, but you also do discover one significant value, and that is subbing x equals 0 into your function. So when we're exploring the function y equals 2 to the power of x, when you sub in 0 for x, you're actually solving for the y-intercept, and you discover a really good solid property that any base to the exponent of 0 is 1. So keep this in mind as we explore other values. This as well just shows you how to break down all of the different points that you're subbing in. So this is a continuation as above. It looks like a lot of work, but it's actually all the same stuff. So when you graph it out, let me go back. It's going to look just like this. So this is y equals 2 to the power of x. Notice that your y-intercept is at the value of 0, 1. It goes really, really close to 0, but never quite touches. And then boom, it accelerates upwards as we go more to the right along the x's. Here is a cross comparison between y equals x squared and y equals 2 to the power of x. Y equals 2 to the power of x you can see is in green. The main difference between that and the general form of a parabola, which was y equals x squared, is that it is unfortunately not symmetrical. It is going to have a y-intercept at 1, and then it's going to go accelerating from there or decaying depending on what your graph is doing. And of course, it will depend on what your base is. So all of this is all the same question up to here, okay? So another key to this, there's no x-intercepts. It's never going to cross the the x-axis or the horizontal axis. There's no max or minimum points because it continues forever. So realistically, the only actual property that we can bank on is that the y-intercept is 0, 1. Now, we're not going to deal a whole lot with our fractions as our bases, but you can try the same thing with y 1 over 2 to the power of x. When you sub in positive points, you're going to notice your graph gets very much smaller. So for example, when you sub in x equals 3, we know from exponent laws that 3 gets distributed to both the 1 and the 2, giving you your y value of 1 over 8. This is called a decay function, and it's actually the exact same. So there's no x-intercepts. You can try the chart on your own if you like, but there's no x-intercepts. The y-intercept is still 0, 1, no max or min, etc. So the only difference is it's changing direction, but same amount of steepness. So this is actually a part of your discussion piece, so we won't go too far into this. This is the graph you're provided with. You're going to explore some of the similarities and differences between these graphs. Hint, hint, it's the y equals 2 to the power of x, function, and y equals 1 over 2 to the power of x. So what you're going to do is you're basically going to try the exact same thing with y equals 3 to the power of x and 1 over 3 to the power of x. Okay, so how you could do this is you could have Desmos open. You could go to graphing calculator and you could actually type it in. So because we're online, it's understood that these are some tools that you might use. And that's completely fine, right? We know you have access to them. So why not use it to your advantage? So you can basically type in any function that you need. Just be super careful of what brackets and such that you're using, and making sure, of course, that everything lines up pretty well. So if we go here, 1 over 3 to the power of x, and you notice a very similar situation, just like we saw with the base of 2 and 1/2, 3 and 1/3. They're going to be completely flipped of each other, and notice the exact same property, that y-intercept exists at both 0 and 1. If we zoom into the graph, what we'll notice, it gets so close to 0, but it never quite touches. Okay, it's hard to see right now, but it never actually physically crosses x equals 0. What it's called is an asymptote, meaning that it gets infinitely close to the axis, but it never actually touches. Okay, so that's one of the explorations you're going to try. So this just really goes into more detail. It compares y equals 3 to the power of x, which is the green, and y equals 2 to the power of x in red. Notice the larger that the number gets, the steeper that the slope, or I shouldn't even say slope, we're nonlinear, the steeper the graph gets in general. Okay, and then of course, you know, you could go even higher, 10 to the power of x, or even just 4 to the power of x. Well, you'll notice those that as that b value or your base value in your exponential gets larger, your graph is going to be steeper. Alternatively, if your fraction is smaller, i.e. getting closer to 0, we would describe that as flatter. So a lot of this is just comparing some different functions. We have a special case at y equals 1 to the power of x, which of course will just produce a straight line. However, you don't really need to worry about this. It won't really be on like your quiz or anything. So it's kind of understood that that will just be a flat line. So there's a lot of extra information. Again, when you are comparing, just make sure you're using the verbiage of flatter and steeper. There's a few try it questions. Remember on Desmos that you can graph more than 2 at a time. You could graph all 5 of these lines, right, if you wanted to. The key is anything raised to the power of 0 is 1, so they're all going to have the same y-intercept. Just some will be steeper and some will be flatter. Okay, so it does have you using Desmos. It's good to try a few practice questions, but again, I'm not too stressed about like the long, tedious calculations with subbing the point in. On Desmos, you can actually sub a point in, so I'll show you that in 1 second. And you could also determine these functions, if it is exponential based on a common ratio. it will describe it in here. So you'll see there's first differences for some of the functions, second differences for table B, but table C, what you're actually looking at is that they are different first differences and second differences, meaning it's not a linear or quadratic. Therefore, automatically it's going to be an exponential. In our course, we only really deal with exponentials, quadratics, or linear. You'll notice that the second differences is 1, 2, 4, 8, meaning that's constantly doubling. And this is called a constant ratio. So you'll notice this, the ratio of the first or second differences, they're all going to be essentially doubling each time. Okay. So for the consolidation piece, all you need to do is contribute to the discussion area linked in today's announcement. If you want to sub in any points to your function, for example, if you wanted to see what the output is, let's say at y equals 3 to the power of x, you could always, and you don't have to retype it, you can either leave the graph there or just plug some numbers in. I'm just doing 3 and then to the power of and whatever value you like. So 3 to the power of 3 is 27. And look at that. As we zoom into x equals 3, we're going to be going up a while, of course, because we're accelerating. And that intersection point is 3 and 27. You really don't need to do a whole lot of calculation for this part. It's mostly just comparing the different functions here.